Okay, in this video I'd like to talk about pulse spreading in optical fibers. And basically we've had all of the ingredients that we need to do these calculations. We're going to get one additional equation that I'll show you here in this section, but essentially we're summarizing material from several earlier chapters. First of all, in Chapter 3 we talked about material dispersion, where n is a function of wavelength, that is, the refractive index is a function of wavelength. And we went ahead in Chapter 3 and went so far as to show how material dispersion gives rise to pulse spreading. And then we talked about pulse spreading per unit length, because the amount of pulse spread is proportional to the length traveled in the fiber, and showed how that gave rise to bandwidth distance products. Okay, so we started off with a pulse spread delta tau, but then we said, okay, we don't want to, we're going to go ahead and divide by L so that this is a value that characterizes our fiber. And so we have delta tau per unit length, pulse spread per unit length. And this was equal to negative material dispersion times the spectral width of the source, delta lambda. And so in Chapter 3 we just had m was due to the material dispersion only. And we were able to go ahead and make some calculations, but what we did was we showed that this gives rise to the rate distance product being essentially a constant, whatever that dispersion per unit length is. And that rate distance product is inversely proportional to the pulse spread per unit length. So it's good to have a small pulse spread per unit length. And that's why it's good to use lasers instead of LEDs, because they have a small delta lambda, giving rise to a small pulse spread per unit length, giving rise to a large bandwidth distance product. And we wrote down the bandwidth distance products for RZ and NRZ signals, and we also related that bandwidth to the 3 dB bandwidth as a frequency. You know that data rates and frequencies essentially have the same units. Frequencies are in hertz, data rates are in bits per second. In any case, you have the per second in both of them. And so we had these equations, and these are fundamental to system design. And now what we're doing in Chapter 4 is we're adding to this story the waveguide dispersion, where what we found was when we made our mode plot that n effective is now also a function of wavelength. And that gives rise to a waveguide dispersion component. We also saw in Chapter 4 that when we have multiple modes, that those modes essentially all have different effective indices, and that gives rise to modal distortion, which also contributes to the total pulse spreading. And these different components contribute using these equations, which I've already shown. The dispersive part of the pulse spreading per unit length is given by the total dispersion times the spectral width, where total dispersion is simply the sum of the material and the waveguide dispersions. Okay, and then we take the dispersive pulse spread per unit length and add it to the modal pulse spread per unit length, but we add it in the squared sense using a Pythagorean type of addition, because in fact these two can never cancel each other. Okay, so they add in this funny way. Okay, and so what we haven't really shown in any of the slides is the relative size of the material and the waveguide dispersion. So I'll show you a couple plots from the book now. On page 69 we have the material dispersion plot, and you can see that material dispersion really does have a zero dispersion wavelength at 1300 nanometers, or 1.3 microns, and that it's as high as about minus 20 picoseconds per nanometer kilometer at 1550 negative, and it goes up all the way up to several hundred, or at the 850 nanometer, it's up near 90 or 100 picoseconds per nanometer kilometer, quite large there. And so those 850 LEDs really limit us when they have that wide spectral width. The waveguide dispersion, on the other hand, depends on the type of waveguide, but for a step index is shown on page 150, a plot, and you can see it's much smaller than the material. And so here is a plot showing the waveguide dispersion versus lambda, again in microns, and showing the range here is from 0 to 5. So you can see this is much smaller. And this is always positive, and so up in this range of 1.5 to 1.7 microns, what we're seeing is that the material dispersion is negative in that range at 1550, whereas the waveguide dispersion is positive in that range up at 1550. And so the waveguide dispersion tends to shift the zero dispersion point a little bit further up from 1300 nanometers when we have a real optical fiber. Okay, a couple of equations that we can write down to further this picture and to give you the total picture is that delta tau by L modal for step index fibers, well, we've already seen this equation, is N1 delta over C, and that delta tau by L for GRIN modal for GRIN fibers is N1 delta squared over 2C. Okay, so these two equations are important. This first one we had back in Chapter 4. It was just given to us. And here in Chapter 5, they just give us the equation for the GRIN. But what's important is to note that the GRIN delta tau by L is much less than SI delta tau by L, due to the fact that it's essentially the same equation, except it's another factor of delta over 2, since deltas are small. So the delta for most waveguides is on the order of a few percent at most, typically less than 1% even for the fibers we look at. So this is why, so this equation tells us why essentially all multimode fibers have a GRIN index profile, because it lowers the pulse spreading per unit length by a factor of maybe 50 or something like that. Okay. And so finally we have a fairly complete picture of pulse spreading in optical fibers. What I'm going to do now is I'm going to show you that we can put all of this together into a spreadsheet, and this is in the handout from Chapter 5, and I hope you can read this here. I hope it's not too small. But basically I've made a spreadsheet, and I'll sort of talk you through the calculations that go into this spreadsheet. And I will recommend that you make a spreadsheet like this and you use it for the problems in Chapter 5, as I mentioned in the homework.